Okay, so we're recording. Time to get started. So last time we were talking about section 1.6. Well, we did some organizational stuff and overview of the course, etc. But getting down into the actual book material, we finished 1.6. So we're going to pick up now with 1.1 and go pretty much straight through for a little while from this point. So anyway, here we go. Section 1.1 is not a whole lot for me to say. Y'all had a course in linear algebra. I believe you should understand basics about vectors. A couple of things I'm going to say. The book uses bold to distinguish vectors from scalars, which I suppose is fine, but it's not something you can do while you're handwriting, and so in some sense they're setting a unachievable example. So I've always thought that was weird. I don't really know why they do that. The very common alternative is, as I have written here, just put a little arrow. You don't even have to make it a full arrow. Just putting the one little barb on sort of the top side of the arrow, if you will. Very common alternative notation for indicating that something is a vector instead of a scalar. Cultural point. Another very common choice is to just not write any distinction. And then it is understood that the reader is supposed to know that this is a vector because when V was defined someplace previously in the book or paper or whatever, they said, hey, V is a vector. And then it's your job to remember that. But in a first time single variable, multivariable calculus course, I like to put the vector hat. I think it helps students to kind of keep track of what they're dealing with. Okay. All right. Next thing I'm going to say, and again, this is just kind of a personal preference thing, but this vector right here, it goes from one given point to another point. The book represents this as what I've got written here, sort of P1, P2 with an arrow over both characters. You can do that. I have a couple of problems with it. One problem that I have is, as written, it kind of makes it look like they're talking specifically about this arrow that literally starts at P1 and that it literally ends at P2. But keep in mind, that's the same vector, as is that, as is that. Those are all the same vector. And so why use a notation that seems to isolate, in particular, a specific arrow, when in fact, very likely, more than likely, we're talking about the vector, which is kind of all of the arrows. So I don't personally prefer that notation. The book uses it. You're welcome to use it, I suppose, but I think it's disadvantageous. The other thing, another alternative, and this is what I strongly prefer myself, is to write it as a difference. Write it as P2 minus P1. Keep in mind there is this natural correspondence between points and vectors. So when we say P2, I mean P2 here is written, drawn on the picture, you might say anyway, as being a location, therefore a point. But you can choose instead to think of it as being a vector, the position vector for that point. Right, so that's an option. And P1, likewise, you can think of, instead of just being the point, you can think of it as being that position vector. And so then the green vector that we're interested in the first place, you can see from this, the sort of the vector algebra of this picture, it's very reasonable to write that green as P2 minus P1. And what's the trade-off? What's the difference? I mean, with color, I suppose that this does, if you're looking at the comparison between these options, there is one extra minus sign, right? A little bit more to write, but I think it pays off because in what I have written here, you can see the algebra. Algebra is a good thing. If there's algebra involved in what you're dealing with, you want to know that. You don't want that concealed and hidden away. You want to see the algebra so you can use algebra. So I have a strong preference myself for that one. and this one over here. Again, the book does it, and that's fine. But I think it's not my preference. Okay, how are we doing? Is everybody with me? That's all I've got to say about 1.1. So moving on. 1.2. Keep in mind, when I say that's all I have to say about 1.1, what I mean is y'all can read the rest of it in the book. So do make sure, I think it'll all be review, but do make sure, flip through, make sure that it is indeed all review, and you're responsible for making sure that you're good on all the rest of that stuff. Okay. 1.2. So more stuff about vectors. More stuff, a lot of which I think you've already seen, and y'all can read and review on your own. The main part of 1.2 that I think you might not have seen before is parameterizations, or if you have seen them, maybe you haven't seen them as much as we're going to need for you to know about them. So I am going to talk a lot about parameterizations here. It'll be most of what we're going to do for the rest of today. So first of all, what is a parameterization? It's a function that gives position in terms of a single parameter. So now, very often that single parameter, very often we call it t. We think of t as being time, and it's a great little conceptual crutch, because if you think of the parameter as being time, and therefore you have position as a function of time, well, that's what drawing is. Right, if you think about it, the action of drawing something, right? Here I'm about to draw a curve. Notice that I start with my pen in a certain location, and then as I draw, position is changing with time. Right? So a parameter is, if you think of your parameter as being time, then a parameterization is just the act of drawing that curve. So that's pretty satisfying, and that's why we tend to use t. Okay, let's see an example. Here we go. That is a parameterization of something. Notice that it gives me x and y, aka location, position vector x. It gives me that as functions of time. Right? We have explicit formulas for what those functions are. Position as a function of time. Coordinates as functions of time. And so this is a curve. This describes the action of drawing a certain curve. Next natural question, what curve? Right? There's different ways that you can use to figure out what curve is being drawn by a parameterization. I'm going to show you several different ways that are useful in different circumstances. There's a metaphor that I use a lot in teaching math, and it's the idea of tools in a toolbox. I'm going to show you like 3 or 4 different ways to take a parameterization and, at least in some cases, conclude what curve is being drawn. Some of them are useful in some circumstances, others are useful in other circumstances, and, well, that's how tools work. Right? If you have a toolbox full of tools, it's not because any one of them always does the job. It's that some of them are useful. Screwdrivers are really good for screwing and unscrewing screws. They're not very good for hammering in nails into a board. Right? So, anyway, I'm going to be giving you various different tools. Okay, so, first tool. Try to find an algebraic relationship that's satisfied by the parameterization. For example, notice x being cosine t. If I were to plug that into there, right, and y being sine t, if I were to plug that into there, well, it works. Right? We have here an algebraic relationship satisfied by these formulas for x and y. It's the old Pythagorean identity. Right? So what that tells me then is that as I draw this curve, whatever this curve is, as I draw it, my pencil will never move off of this unit circle. which is pretty strongly suggestive that we're drawing the unit circle. Does that make sense to everybody? Is everybody happy? Is everybody following? Okay, so the lesson to be learned here, if you find yourself looking at a parameterization, you want to know what this parameterization is, look at the formulas there and ask yourself, do you know, off the top of your head perhaps, any convenient algebraic relationship between those things? And sometimes you get lucky, such as in this case, we look at sine and cosine and we remember, oh yeah, that's why there's that Pythagorean identity thing. And that causes you to realize that you're talking about the circle. Okay. Of course, very often, you won't have exactly these formulas. You'll have something different. There won't be any obvious relationship, and this doesn't work. All right, next example. Here is a parameterization. How do we figure out what that is? Again, there's multiple ways to do it. I'm going to show you two different ways that work for this one. First one is a neat little trick where, don't forget, keep in mind, that first coordinate formula is telling you what x is. This second coordinate formula is telling you what y is. And the big trick here then is to solve for t. My elbow hit the thing. Sorry about that. God, that's jarring, isn't it? Solve for t in one of them, let's say the x formula, and then take that formula for t and plug it into the second relationship. Right? So, in doing so, notice that the punchline is that you have eliminated t from the algebra, multiplied out collect terms, and what you end up with is an equation satisfied by those formulas. In other words, you found an equation for whatever it is that's being drawn by this parameterization. Everybody see the process there? Solve for t in one equation, plug it into the other equation. All right. So, this worked great in this circumstance. Let me point out, though, that sometimes, looking at, okay, here's my formula for x, how do I solve for t? Sometimes that's a harder question. Here it was trivial, but, what if the formula for x was a, degree 5 polynomial of t? And you can't solve for it, and this method crashes and burns. All right. Okay, here's another method that you can use, and that is to kind of look for a relationship between x and y. So in particular, don't forget that's x, that's y. So looking at your formula for x, looking at your formula for y, do they kind of look alike? Do I see any clear, easy connections between them? And what I notice in this case, between the relationship between these two formulas is, they're both like, some constant times, single power of t plus some other constant. They're both kind of, they fit that same, they're degree 1 polynomials of t. So they have a lot in common in that sense. So the idea then is take the algebra describing x and try to figure out how you can manipulate it to turn it into the algebra describing y. Right? Look for how would you turn the first t formula into the second t formula. Right? Now in this case, it's pretty easy to do. You take the t minus 1, multiply both sides by 3. That starts to make this look more like that, because you get the sort of the lead coefficient right. Then after that, add 7 to both sides, and sure enough, we have done some algebra to turn that into that. Or said differently, we find ourselves now with something you can do to x to make it equal to y. In other words, we have an equation relating x to y. So, different way to go about it, right? Very different from this first method. Well, I guess this is actually our second method. This third method is different from this second method. And again, sometimes, even though this might not work, this might still work great. So, for example, again, we speculated, what if these formulas up here were great big nasty polynomials? You're dead in the water. You could not begin to solve the t. But you still might find some easy relationship between it. It could be as simple as, oh yeah, y is exactly 4 times x, or something like that. Right? It could be that there's a really easy connection in this sense that you won't ever realize in that sense. Okay. All right. Moving along. See a 3-dimensional example. So here's a 3-dimensional parameterization. Clearly 3-dimensional. We've got 3 coordinates. So this is not drawing a curve in the plane. This is kind of drawing, if you will, a curve in space. Right? So curve in space. Again, tools for your toolbox. Here's something that works in this circumstance. I happen to notice, I get lucky sometimes, I'm just happening to notice that that part I understand. Right? Cosine sine. I mean, that was our first example. It was like 10 minutes ago. So, what is that? I can't just throw away that third coordinate. Right? But what I can do is say, look, if I were to throw away the third coordinate, we would no longer be looking at the same curve. We would be looking at its projection down into the XY plane. We'd be looking at its shadow, if you will, down in the XY plane. Right? And, cool, because I know exactly what that shadow is. Again, this is why I started down this road in the first place. I see that cosine sine. I like it because I know that's tracing out a circle. So, still don't know what the curve is. Ignore the fact that the picture is already here. Okay? But even though I haven't concluded yet what the curve is, I know that its shadow is going around counterclockwise in the XY plane. What do you think? Everybody good so far? Okay. What else do I know? Well, I can look at this part here and say, golly, that sure does look easy. Just the z-coordinate, it's t. I mean, the really easy formula. So what sense does that make if I look just at the z-coordinate? Well, in fact, that, if you think about it, is telling you the projection to the z-axis. It's ignoring x and y, throwing away x and y, looking just at the projection to the z-axis, which is just keeping track of the height. And again, that's something that's pretty easy to understand. This formula here, t, I mean, it just starts at 0 and just kind of starts moving upward. Right? So that projection to the z-axis, also easy to understand. And neither one of these observations answers my question, but together they kind of do. Think about it. What curves possibly could there be that have shadows that are going around in circles in the XY plane and are then rising at a constant rate? And I appeal to your geometric intuition. This curve here, this helix, right, like a stretched out slinky, right, is the only such curve. So this is what this is parameterizing. So this parameterization. Let's see if I can do this. Gives me a helix. Everybody happy? Tool for your toolbox. I mean, if you should happen to notice that there's a nice, convenient projection, some of the coordinates are easy to understand, this is a good foot in the door. Okay. All right. So, I'm going to turn now to a different question about parameterizations. Actually, I'm going to come back up here and real quick point out that what we did in this question is we were given a parameterization that was given, and what we tried to figure out is what's the curve. So we were going as if you will, we were going this way. So what I want to talk about now is what if we're going the other way? What if we're given a curve described in some way, whatever, I don't know. And if we want to conclude from that what is a parameterization of that curve? And so, like I say, it's the opposite question. We're going the other direction here. So this process of taking a curve, described somehow, and creating a parameterization, this is called parametrizing. Parametrizing the curve. Okay. So how do you parameterize a curve? And again, there's different tools that work in different cases. There is no single method. I'm going to try to fill up your toolbox with tools between the collection of which hopefully you can piece together a parameterization of what you need. There is, this is just a by hook or by crook kind of situation. So I'm starting with my favorite one. If you had to pick a single parameterization method to, use only and exclusively for your whole life, of course you would be very limited. It wouldn't work for every situation you encounter. But if you had to pick one, I think I'd pick this one. I call it the graph parameterization. Very importantly, this only applies if the curve that you're trying to parameterize is a graph. And we're going to say more about what graphs are later on, but for the purposes of what we're doing now, let me just say you can solve for one of the variables in terms of the other. So here I'm presuming that we know y as a function of x. That's what we mean by graph. Okay. So, you find yourself in this circumstance. Here's the extremely simple and effective method for parameterizing, and that is let t just be the input variable. It's as simple as that. Whatever is your input variable, in this case, x is your input variable. Just let t be x, and everything will just fall into place. It just works. So here we go. Let's see an example. Here we go. We have y as a function of x. Right, so we've solved for y. We're going to let t be the input variable. So x is equal to t. And now what? I've got x equal to t. How am I going to figure out what y is? Well, here's the thing. X is equal to t and y is equal to x squared, and that pretty unavoidably means that I have to choose y equal to t squared. Does everybody see how that kind of fits together? And it all comes out of making this one choice, right? The act of choosing for t to be the input variable immediately gives me one of my coordinates as a function of t, and it basically forces me, by the given equation, into what the other variable is going to be in terms of t. And we declare victory and move on. What do you think? Everybody okay with that? All right. Really good trick. Here's another example. This one's a little trickier. This does not look at a glance to be a graph. And you can try to solve for y, right, as, alphabetically we tend to do, but you're going to get in trouble if you try to solve for y. You can't. This is transcendental in y, and you cannot analytically solve for y, right? So what you can do, however, is you can solve for x pretty easily, right? And so even though it's sort of a weird graph, it's a backwards, x is a function of y instead of y being a function of x. But that's just that's alphabetical order. It's not set in stone. That's not mathematically significant. I'll say that. So we have a graph. One of the variables is a function of the other. Let t be the input variable. The input variable is y, so we're going to let y equal to t. And then, well, again, everything just kind of falls into place. Everywhere I see a y, I put a t, and therefore x has to be that. And we win. We have ourselves a parameterization. There you go. That is a parameterization of the curve described by that equation. How you doing? Everybody happy? Okay. All right. Then this next one's intricate. There's a lot of details in this next one, but there's also a big idea. The very first thing I'm going to say about this example is what the big idea is. The big idea is use vector algebra. Sometimes vector algebra allows you to take something that on its own is prohibitively complicated and break it down into pieces, each of which is highly tractable. Where the whole is more difficult than the sum of the parts. So that's what's going to happen here. Now let's dive into the example. We have a wheel. I like to think of this as a bicycle wheel. The wheel is sitting on top of the x-axis. It's rolling to the right, like that, which means the wheel is rolling that way. And as it does so, if you were to imagine a reflector attached to the wheel there and ask what is the path followed by the reflector, right? And then if you were to ask how would I parameterize that curve, well, this is a pretty ugly looking curve. And this is why I like to think of it, by the way, as a bicycle wheel. You all have probably seen this at some point. If it's dark out and you see somebody riding by a street light on a bicycle, there is indeed a reflector, usually not on the rubber of the wheel, but near the rubber, and that reflector will pretty visibly make this kind of jumpy, weird curve that looks kind of like this. Everybody with me? Okay, so how are we going to parameterize this curve? By the way, quick side note, if you were to say, I don't like parameterizations, I want to try to find the equation of this curve, you are out of luck. It is intractable. I don't want to say impossible, but it is not. You're not going to find a convenient equation for this curve. But parameterizing is something that we definitely can do. So here's the big idea. Again, the big idea is use vector algebra. And the way vector algebra is going to show up is by the fact that the reflector can be thought of as a sum of two simpler vectors. It can be thought of as a sum of the axle, which again you can think of as being a vector, even though of course we visualize it as being a point. But again, we have this. You can think of points as vectors, vectors as points. So we have the axle. That's going to be a pretty easy path to describe. The axle is not hard. Look, it's moving in a straight line. Right? It's a nice thing about bicycle axles. The ride on the bicycle would be terribly bumpy if the axle wasn't moving in just a smooth straight line. Right? So that axle's going to be, we've got work to do, details to be cranked out, but we're not intimidated by parameterizing that axle. And then the next thing is this difference vector right here that I have in green. The displacement between the axle and the reflector. That is also a relatively easy vector to understand. Now, a lot of students get confused and think, well, that arrow is doing some pretty trippy stuff. I mean, it starts like that, and a little while later it's going to be like that, and then a little while later it's going to be like that, and then over here it's going to be like that, and then it'll be like that. That seems hard, right? How are we going to keep track of all these green arrows? Reminder, we don't care about the arrows. We care about the vectors. Vectors do not have location. These vectors are not, I didn't want to erase that one. These vectors are not jumping around all over the page. That vector that I have drawn there in green is exactly the same as that vector. A vector is just a direction and a magnitude. So as this wheel rolls, this D vector is just going around in circle. Right? Or let me draw that a little bit friendlier. It is just going around in a circle like that. So again, circle, not hard, not scary. Details, yes, we're going to have to work out details, but tractable. All right. So now, before we get into those details, Is everybody on board with the plan that we're going to parameterize the axle? We're going to write down an equation for this green arrow that's going to be running around in circles, and then we're going to add them up per this formula here. Everybody's with me? Okay. All right. Okay, what's our parameter going to be? I'm going to use this angle here as my parameter. Now, you don't have to. There are different reasonable choices that could be made. It is a choice what you use as your parameter when you're doing a parameterization. What I like about this as a choice is notice that at the very beginning, when we are starting, when you might say time is 0, right? Notice that this angle is indeed 0. So it starts at 0, and then as the wheel turns, notice that t increases. So that's satisfying, right? We like to think of a parameterization as, something where the parameter, the process of drawing out whatever it is that we're interested in, has t starting at 0 and increasing from there. Right, so reasonable choice. Alrighty. Okay. So now on to the details. How are we going to understand the axle? That axle right there. Here it is again, that axle. That axle moving in a straight line, horizontal straight line. Namely, it has a constant height above the x-axis. Namely, y is a constant. Pretty easy pitch that constant value of y is just the radius of this wheel, which is a, as given here. That's the easy part there. Everybody happy with that? Right. Okay. So now let's talk about the x-coordinate. Where do we get this from? An x-coordinate. This is a tricky argument. This is something that you have to. I'm going to call this an insight. Here's the insight. The insight is that the amount of road that has touched rubber is the same as the amount of rubber that has touched road. Now that's an appeal, intuitive appeal. That's what it means for a wheel not to slip, right? If the wheel were slipping as it was going, then that wouldn't be true. But so we're assuming this is dry roads and straight line, constant speed, and no slipping. So the amount of rubber that's touched road is the same as the amount of road that's touched rubber. Everybody okay with that? Believable? So here's the good news then. This x-coordinate that we're looking for, the x-coordinate of the axle is the same as the amount of road that has touched rubber, which is therefore equal to the amount of rubber that has touched road, which is an arc of a circle. High school geometry tells us how to compute the length of an arc of a circle. It's the angle times the radius. The angle is t, the radius is a, and so that is at. Everybody go to that? Again, this was a tricky bit, insightful point about road and rubber and all that, reducing the x-coordinate question to a high school geometry problem. Okay. All right. And we are halfway there. We've got the formula for our axle. Our axle is parameterized by that right there, which we will eventually toss right into there. Okay, let's move on to the next part. Next part, we are now going to look at, going back to green here, we're going to look at this difference vector, which again is kind of going around in circles. And here's a picture of that. So here's that same vector drawn in standard position so that we can deal with it more conveniently. Tails at the origin, so the point is the vector. The point that is the head of the arrow is the vector that arrow describes. And how do we describe this point here? this point here? Well, it's a point on a circle of a certain radius, and cosine theta, sine theta, and don't forget to multiply by the radius. Right? It's an easy trig there. A cosine theta, A sine theta. Keeping in mind the annoying fact that that's in terms of this angle, theta. Right? Cosine and sine are based off of angles measured off of the positive part of the x-axis. That's not t. T is this angle, not this angle. But anyway, we got some algebra on the page here. We've got a formula for d. It's just in terms of the wrong thing. So conveniently, I can write down an easy formula for theta in terms of t based on the fact that these two angles always add up to 3 pi over 2. Whoops. Try that again. They always add up to 3 pi over 2. The bigger t gets, the smaller theta gets. So if they add up to 3 pi over 2, you can solve for theta. You take that formula for theta, you plug it in here, and d is then a cosine, we have this angle addition circumstance. And I hope you all remember your angle addition formulas. Let me rephrase that. I am aware of the fact that most of y'all have forgotten your angle addition formulas, and I urge you to refresh yourself on those. There is a lot of stuff in trig classes in high school that's maybe a little on the obscure side. You're not really going to need. Angle addition formulas are not in that category. Angle addition formulas are really handy. So please do, polish off your memories of angle addition formulas. It's going to be really useful here and there. Here, for example. Okay. So using the angle addition formulas, we can rewrite this algebra as that. And so there's my D vector. And we're done. We've got a formula for D, previously derived a formula for A. The reflector that we were interested in was the sum of those two, and we are finished. Everybody all right? Yes.
Just a question about the notation.
Yeah.
The D that you wrote is just like an actual D with the vector symbol like in the middle of it?
Oh, well, yeah, I understand your question. This notation here, I shouldn't use orange. Let me use black. That'll be better. Okay, so that, there's a D, and then, I could have put the little arrow up there, but it's just really far up there, and it just makes it kind of tall, so yeah, I just kind of do like that. Yeah, right. Yeah. Good question. Anybody else? Everybody's happy? All right. So if you want to practice problem or something to see if how well did you digest not just the details of this specific example, but the general idea of how to use this kind of vector algebra to understand a curve like this. Tweak the question and then try to solve that tweaked version. So, for example, maybe instead of having the reflector on the edge, right? What would happen if the reflector were sort of halfway down? How would that change your question? The curve would then be it'd be a pretty different curve, right? And what is that? How do you get your hands on that? What details change? What details don't? Right? Something to think through. All right, moving along. Parameterizing a line. This is a standard trick, but nice to know. Suppose that you have a point on the line, and suppose you have a vector parallel to the line. And this is fairly often the case, that you've got some line that you need to understand. You don't have an equation for it. You don't know a parameterization. You don't have any algebra describing it. All you know is, it passes through a certain point, and I know what direction it's going, and that's really all you know, right? So how would we use this information to parameterize the line? The big idea here is to note that every point on the line can be thought of as a sum of that given point, and then, not the vector you were given, but something that is parallel to the vector that you were given. Right? So in other words, a multiple of that vector that you were given. Right? So every point on the line that I have in purple here can be thought of as, dark blue plus dark green. Right? And there you go. There's a parameterization. As it turns out, we have position, therefore x, as a function of just one parameter, which, I saw this coming, so I chose that parameter to be t. Anybody on board? Yes?
X not, even though it's a point, it's still a vector.
Yeah, that's right. So you got to make sure to remember that there's a duality between points and vectors. Let me just give myself some space to. Okay, I can do it right in here. So when you have a vector, right, and let's say that vector right there. That vector you can think of as being a point, and the rule is. First of all, keep in mind vectors don't have locations. So this is just one arrow representing my vector. That's the exact same vector. So is that. So is that. So is that. That's a single vector. And the point that it corresponds to is the head of the arrow representing the vector whose tail is at the origin. So I don't need any of this nonsense anymore. I'll get rid of that. This vector corresponds to that point. Whenever you have a point, you can, in this way, associate to a vector and vice versa. And you kind of have to, because if you want to, for example, if you want to add a point and a vector, I don't really want that to be a separate formula from, okay, but what if I want to add a vector and a vector? Do I need separate formulas? This is kind of annoying, right? And so we kind of blur the distinction between points and vectors. Yes, they're different, but we can treat them, we can blur the lines for the purposes of algebra in ways like this. Is that satisfying?
Yeah.
Okay, cool. All right. Good stuff. Okay. Here's another one. So sometimes the thing you want to parameterize is not that different from something you can already parameterize. So for example, suppose you want to parameterize this ellipse with that equation, which you all remember from Algebra 2, looks something like that. How would I parameterize that ellipse? Here's the thing. Ellipses, known fact from high school algebra. Hopefully you remember this. If you don't, hopefully you're willing to believe me when I say this. Ellipses are just the result of stretching a circle. So, here's the thing then. This ellipse is actually a pretty similar thing to this circle, which I already know how to parameterize. Right? Unit circle, easy to parameterize. Again, that was our first example. So I have the orange parameterization of the circle. All I need to know is what happens to that parameterization when I stretch it out however is needed to make this ellipse. And conveniently, that stretching process is pretty clear. I'm clearly going to have to stretch by a factor of 3 in the x direction. And so stretching by a factor of 3 in the x direction, that's where that 3 comes from. I'm just taking, taking this original orange parameterization, stretching in the x direction by a factor of 3 just by literally multiplying all the x coordinates by 3. Everybody good? And then I can likewise stretch by a factor of apparently 2 in the y direction. There you go. I'm going to multiply all the y coordinates by 2 by just sticking that 2 in right there. So we took a parameterization that we already understand, tweaked it accordingly to give us a parameterization of a new thing. Okay. again, tool for your toolbox. Some of these are specialty tools that only get used in narrow cases. Some of them are broad tools that are used in a lot of cases. You got to have all your tools. Okay. All right. Now, I want to take a step back and let's remind ourselves exactly what are we doing here. We're trying to understand curves. And we have algebra that helps us understand curves. Our new algebra for understanding curves is parameterizations. Older algebra that we have for understanding curves is equations. A lot of people look at equations and parameterizations and don't really see the difference. After all, they're both algebra and they both describe curves. So it'd be kind of easy to say, whatever, a parameterization is kind of an equation. But they are very, very different in how they relate to the curve. So here we go. Specifically, a parameterization. Here's what a parameterization does. A parameterization takes a parameter as the input and then spits out a point as the output. So the way I like to think of this, I like to think of a parameterization as being a point generator. It's taking some arbitrary, otherwise meaningless number t and doing stuff to t, and out comes I have created a point on the curve. So, point generator. Okay, that is not what equations do. Equations do not create points. Equations are what I like to call point testers. An equation, you take the point, whatever point that may or may not be on the curve, you haven't decided yet, I don't know. Take that x comma y, you can plug that into the equation, and then the equation, it either works or it doesn't work. Right? Either both sides of the equation are equal, in which case, yes, the equation worked, that means the point is on the curve, or no, the equation didn't work, the two sides of the equation aren't equal, that point is not on the curve. So, both involve points on the curve, but in very different ways. And so again, parameterization is a point generator, an equation is a point tester. Everybody see the difference there, the distinction. Very important distinction. By the way, this leads to a terminology gripe that I have. Some people refer to parameterizations as parametric equations. And, there's an equal sign. So, technically it's an equation. But we need to distinguish between these two very different roles that these two very different pieces of algebra do. Right? And so I strongly prefer the word parameterization because while I'm trying to distinguish something from an equation, it'd be nice to not have the word equation in the thing that I'm trying to make distinct from it. Right? It's confusing. So anyway, when you see parametric equations, I encourage you to think parameterization. All right. So what I'm going to do then is use this distinction in the next example, noticing that when you parameterize, a point comes out. The way you use an equation is to put a point in. Let's see if we can use that to solve a problem. And here it is. I have here, I've already forgotten what colors I used. Sorry about that. But here is a parameterization of some curve, some wacky curve. I don't know what that is. It looks kind of parabolic maybe. I don't know. It's hard to say, isn't it? But some sort of a curve there. And I want to know, where does that intersect this plane? Now, notice in the statement of the question, it didn't explicitly say that this is a parameterization. And, it's just, here's this thing, which points are on this plane. So, we recognize though, and it's, part of your job as a student is to recognize what are these things that I've been given. And I have a thing that spits points out. I have a thing that eats points in. And we're going to literally put them together. So we're going to generate points with the parameterization, thus giving us points that are on the curve. And what I want to know is which of those points on the curve are also on the plane. So I'm generating points and then testing them to see if they're on the other object. Everybody good with that? So I'm going to get a little bit of algebra to deal with. This equation right here, of course, you can rewrite as just that right there, collecting terms together. T squared minus 1 equals 0. That's a pretty easy equation to deal with. And that just tells you right out that T is plus or minus 1. So we now understand what the correct values of T are. Let me say the whole thing together. The values of T that the parameterization creates points on the curve, which are also testing positive as being points on the plane, those values of T are plus or minus 1. Now, of course, what the question asked us wasn't what are the values of T. The question asked us for what are the points, and the points are these here. And so the way you would find the points is take the given values of T and plug into the parameterization. And that gives you 2 points that would answer the question. How are we doing? Yes.
How do you get T squared minus 1 equals 0?
Oh, that's just algebra. If you collect terms together from there to there. Boring, tedious algebra that you can do yourself. Yeah.
So we only have to plug positive and negative 1 into one of the points.
You have to plug these 2 values of T into these 3 equations. Well, sure, because points are described by 3 coordinates, and so you need all 3 coordinates. Yeah. Okay, we're out of time. Drawing the line right here for today. See y'all on Monday. Have a great weekend. See you later.